In the world of computer vision, tracking individual points across video frames has long been a cornerstone of understanding motion, object dynamics, and scene structure. But most state-of-the-art methods rely on massive amounts of annotated training data that's expensive, time-consuming, and often synthetic. What if we could track points without any training at all? Enter HeFT, a zero-shot point tracking framework that leverages the rich visual priors of pretrained video diffusion models, specifically Video Diffusion Transformers, or VDiT. This isn't just another tracker. It's a paradigm shift, one that turns generative models into powerful perception engines. At the heart of HeFT lies a deep insight. Not all parts of a video diffusion model are created equal. While many researchers treat VDiT as a black box, we dug into its internal workings and uncovered something extraordinary. Our analysis reveals that attention heads in VDiT aren't just parallel processing units. They're specialized functional modules. Some heads are matching-oriented, designed to find precise correspondences across frames. Others are semantic-oriented, attending to visually similar regions. And some are position-oriented, focused on spatial proximity. This isn't random. It's intentional. Each head operates in its own subspace, applying independent projections to queries and keys. The result? A diverse ecosystem of specialized behaviors, where the best-performing head consistently outperforms the entire layer, even when aggregated. But it gets deeper. We also examined how frequency components within these features behave. Using 3D Rotary Positional Embedding, ROP, VDiT encodes spatiotemporal positions through rotations that vary by frequency. And here's the key. Low-frequency components remain nearly invariant across frames, while high-frequency components rotate sharply with position changes. This means low-frequency features encode stable, semantic content, perfect for matching. High-frequency features, on the other hand, capture fine-grained positional shifts, useful for localization but noisy for correspondence. So what happens when we selectively filter out high-frequency noise and keep only the low-frequency signals? The results are striking. Tracking accuracy improves, and in some cases even surpasses full-feature performance. Retaining just the bottom 45% of frequency bands gives us near-optimal results, while removing the top 15% actually boosts performance. This is because high-frequency components introduce instability, especially under occlusion or appearance change. So how do we put this all together? HeFT's pipeline begins with a single denoising step on real-world video inputs. Why one step? Because our experiments show that the final diffusion step yields the most reliable perceptual cues, where the model has already learned to suppress noise and sharpen structure. From that denoised latent representation, we extract features from the best-performing attention head, the one that specializes in correspondence. Then we apply frequency-aware filtering, discarding high-frequency components that carry positional noise. Next comes localization. Instead of hard-argmax, we use soft-argmax on the correlation map. This smooths the output, making it more robust to small perturbations and occlusions. To detect visibility, we implement a forward-backward consistency check. After predicting a point's next location, we trace the trajectory backward. If the forward and backward paths diverge beyond a threshold, we flag the point as occluded, preventing chaotic drifting trajectories. And to combat appearance drift over time, we introduce feature refinement. The query feature is updated using the newly tracked position, ensuring the tracker adapts to changes in lighting, pose, or scale. The result? A robust, accurate, and zero-shot point tracker. No training, no annotations, just pure priors from a pretrained model. On the TAP-Vid benchmark, widely regarded as the gold standard for point tracking, HeFT achieves state-of-the-art zero-shot performance. It outperforms all prior zero-shot and self-supervised methods, and comes remarkably close to fully supervised approaches, without a single labeled frame. Even more impressive, this framework generalizes across different VDiT backbones, from COG Video X2B to WAN2113B, and especially Cosmos Predict 22B, which is trained specifically for video prediction and continuity. That model, designed to preserve frame-to-frame details, excels at tracking, proving that the training objective shapes the quality of learned correspondence priors. But this isn't just about performance. It's about principle. HeFT demonstrates that video diffusion models aren't just generators, they're foundation models for perception. Their internal representations contain a wealth of spatiotemporal knowledge, encoded through head specialization and frequency-based inductive biases. By respecting these structures, by selecting the right head, filtering the right frequencies, we unlock unprecedented capabilities. And while HeFT is currently offline, requiring full video processing before tracking begins, this opens exciting future directions. Real-time online tracking via model distillation, incremental feature selection, or lightweight proxies that preserve the diffusion model's correspondence priors. In a world where annotated data is scarce and real-world video is messy, HeFT shows that the future of tracking might not be built on labels, but on the latent wisdom of diffusion models. It's not about training on more data. It's about understanding the data we already have, deeply, structurally, and intelligently. So the next time you see a video, ask not just what's happening, but how the model knows it. Because in the silence between frames, the diffusion model is already whispering the answer. And now, thanks to HeFT, we can finally listen.